Example, the Brayton cycle with reheating. A gas turbine generating set has a high pressure turbine where it is used to drive a compressor, and a low pressure turbine drives a generator. The air is drawn into the compressor at 100 kPa and 25 degrees Celsius. The pressure after compression and the high pressure turbine are 720 kPa and 400 kPa respectively. The air leaves the combustion chamber at 1100 degrees Celsius and reheated to 1100 degrees Celsius after the expansion in the high pressure turbine. The isentropic efficiency of the compressor is 80% and for both turbines are 85%. Illustrate the diagram of the plant complete with a numbered on TS diagram and determine the cycle efficiency, the work ratio, and the mass flow rate in kilogram per second when 6500 kilowatt output is obtained. Given for you is the specific heat ratio K and the specific heat at constant pressure Cp for the air. The TS diagram for this particular question will be look like this. Since the isentropic efficiency for both compressor and turbines are given from this question, therefore we have to draw the actual states for the Brayton cycle with reheating. Next, we are going to list out all the informations given by this question. Note that process 1 to 2 will consume work, therefore we are going to have the terms work in. Process 2 to 3 is the constant pressure heat addition to our system, therefore we are going to have the terms Q in. Process 3 to 4 is through the high pressure turbine, therefore we are going to have the terms work out. For the process 4 to 5, this will be the reheating process, therefore a portion of heat will be added to our system, therefore we are going to have the terms Q in. For process 5 to 6 is through our low pressure turbine, and work will be produced through this low pressure turbine, therefore we are going to have the term W out. And lastly, process 6 to 1 is the constant pressure heat rejection, and we are going to have the term Q out. To determine the cycle efficiency, we are going to use thermal efficiency is equal to work net out divided with Q in, and we are going to obtain this expression. The work ratio can be determined by using the formula of back work ratio is equal to work in divided with work out. And we can use this equation in order for us to find the mass flow rate when the power output is given. In order for us to solve this question, we need to find the value for the temperature at state 1, state 2, state 3, state 4, state 5, and state 6. The temperature for the state 1 has been given from the question. T1 is equal to 298 Kelvin. For state 2, first we are going to find T2S by using the isentropic relation for temperature and pressure. We are going to get the value of T2S is equal to 523.8 Kelvin. By using the isentropic efficiency for the compressor, we are going to find the actual temperature for state 2. And we are going to obtain the value of T2A is equal to 580.3 Kelvin. The temperature for state 3 also has been given by the question 1100 degrees Celsius, and if you convert to unit Kelvin, we are going to get the value of 1373 Kelvin. For state 4, we are going to use the isentropic relation for the temperature and pressure to find T4S. After we substitute all the required values and calculate, we are going to get the value of T4S is equal to 1185.5 Kelvin. By using the isentropic efficiency for the turbine, we are going to find the value of T4A. Once we substitute all the values and calculate, we are going to obtain the value for the T4A is equal to 1213.6 Kelvin. The value for the temperature at state 5 is equal to 1373 Kelvin. We are going to use the isentropic relation to find the temperature at state 6 for the ideal case. Once we obtain the value of T6S, we are going to find the value of T6A by using the isentropic efficiency for the turbine. Now we can solve the required item requested by the question. Note that P1 equal to P6, P2 equal to P3, and P4 is equal to P5.